Welcome to a new teardown video. This time it's another power supply. Elcanic lab power supply type LR2302. Have you seen this design before? Or something that looks a little bit like this, a 3-in-1 with a meter switch, stuff like this? Well, let me try and put it very close to my good old B&O. I think they look very much the same. I'm not saying they stole the idea or anything, but look, it's the same width. Okay, it's a half a centimeter taller, but it's same features and same everything, right? Except, oh, look at that, 2 amps per output, and still 2 times 30 volts, completely isolated and all that stuff. And now this extra 5 volt output, I guess this is, yeah, it is, yeah, see, 5 volt, but now it's variable current. Okay, so you can current limit this. That is pretty cool. All right, and then the meters, it's the same as the other one, but it's the other way around. Of course it is, because the outputs, they are orientated in another order, right? So this means when you go left here, you take this one, and here it's the other way because they have it out here, maybe to make space for the power switch. So this is how it works. Volts current, AB volts, AB current. All right, and then the C, and we got indicators with LEDs and everything. And I think we're also going to test, or no, we of course we're going to test this, but we're going to see them side by side in the next clip, right? So this is inside the Elcanic. The 2 power boards for the 2 30 volts 2 amps, I guess, right? And then this will be the 5 volt, I guess. That makes sense. They got connectors, they got the transistors isolated on the same heatsink. So heatsink looks a little bit like it's actually smaller when it comes to, it's more or less the same width, right? So this one goes all the way to this side, and it's more or less the same, but this height here is also about 5 millimeters higher. I think they've done a lot of improvement. The transformator is really nice and big, and it's located in the middle of the instrument. That is a lot easier and better when you want to feel the weight distribution, but of course it could be worse when it comes to noise and stuff. Here they got the transformator in one side and can now focus on the nice and quiet areas away from the transformator, so it's a little bit of a different idea. The meters here, they're also mounted on a little piece of mounting here on the back. It's more or less the same, because the meters here, they are mounted here somehow. I can't actually remember how the heck. Oh yeah, okay, they're mounting on the back on the screws, holding them into the holes like that. And there was actually one more thing I wanted to show as a side-by-side compare, because the meter design looks very much identical. Of course they have moved the meters a little bit more in. This is a little bit too close to the side and all that, but see, this type of plastic here, how crazy. See this type of plastic, it's not doing this problem. Isn't that funny? So some types of meters is doing this, while others crazy sensitive. Of course, you're not supposed to touch them, and if you have this problem, just do just put all your Corona on it, and it's gonna be fine. Before I was going to power this Elcanic up, I was doing a little bit of poking around with different things and having a little look here and there and what it got, because I have never seen this before. So, and look at this one. Ooh, that is a little bit too loose. And why is it really loose? I don't know. And why is this directly up a capacitor? It could have been the other way around. They could have been swapped, and then this bridge could have been mounted in the bottom metal. But this is not the smartest way to do it. And also what I noticed, the two 30 volts outputs, look at that. This looks like two relays. So what I think we got here is a multi-voltage level transformator winding selector. So it's a pre-selector, and this is a very, very good and effective way to remove heat from the heatsink and up the efficiency, obviously, so you don't have so many thermal issues. But again, rectifier up the capacitors is just where everybody loves to put them. But this is, oh yeah, this is 2 amps now. So, and also what I noticed, the outputs, they're not feedback from the outputs, no, but at the end of this cable all the way here. So that is a thing to improve feedback directly at the outputs. This is what you want. You want 0 milliohms output impedance directly at your output. Maybe this is not a big deal to some, because they got 5 more meters external, so this 20 centimeters is probably not a thing, but it's not good for the specs, at least, right? And we got the usual trimmers for probably the meters or something like that. I'm not too impressed about the distances or the safety distances or lack of it, right? Between the potmeters, wires and stuff like that. Also, what I see here, see, this is the voltage output. So when you crank up the voltage, what are you doing? Let me show you guys this. Maybe it's easier to see here in the front. Okay, so this is more voltage this way, right? And more voltage means, see, we go to the more open side of the potmeter. And again, this pin is not connected. This one should of course have been connected to the sensor pin. So if there's a lift, we at least get that voltage and not out of range voltage. Yeah, but a really, really good design would have been the 2 wires here. So that means when you have an open slider in your potmeter, you'll get 0 volts output, because that is the non-dangerous error. We don't want to have the dangerous error of full output voltage. Imagine you're playing around with your 3 volt product down here, and then suddenly kapoof, just because there's a little bit of a booger in the pot. No. PCB layout is really beautiful. I don't see any fixes or mods or any funny stuff here. It all looks, yeah, just as it's supposed to look. And this is the 5 volt supply from the back. All wires and stuff, it's neatly mounted here. Again, a thing to consider, This is the mains transformator with all the AC going here. And then all this AC and stuff. Look, your output transistors and those wires, they're supposed to be super clean, noise-free, ripple-free, and all the good stuff that you're paying big money for. Those wires are just directly paralleled. Look at that. With all your ripple, high peak pulse currents and stuff. That is not how you do it. You don't want that. But it looks sexy, but it's just a bad way to do it. It's the wrong way to do it. I always promised to do power up on video, just in case there is a little kaboom. 9 watts of idle. Most likely not enough to cause any big sound effects. I really like this ABC. That is absolutely great. And those are the really those are the LEDs I love. Old LEDs. I know they're so... I don't know if you can see this. I guess you can't see this on a video, but the glow is just deep red. Really a sexy color. But yeah, in the video it looks a little bit purple. But wow, that color is great. So yes. Ooh. See? Two. Okay. Oh, and I don't know if this voltmeter is right, but did you see this? The pot is on 3/4, and then we got maximum. Ooh, and I can continue hammering up the pot. Oh, this is half, and then we got 20, and it's unstable. Like, okay, this pot is just click clack. Okay, we need to use this pot a little bit more. So that was this pot. Let's go to the next one. Ooh, why don't we see any volts? Ah, okay, it's because... Okay. Oh dear. Is this convenient? I see both of the voltages, but I don't see the currents at the same time. So, oh, now I see the currents. Okay. I don't know if I like that or not. And that will be... Ooh. So this current limit goes all the way to 0. Okay, that is nice. I like that. So, oh, this one also does that. Okay, let's go for volts. And then play with, yeah. So all the way down is 0. So that is great. They go to 0. And also that one. Great. That is really nice. This we like. 0 current output. And pots that needs to be replaced. Okay. But I feel we're going to do the same test as we did with the B&O. We're going to give this 3 amps and we're going to load it with 3 amps for an hour. And we're going to come back and see if there's any smells. Let me see if I can show you guys this. You can see this is the capacitor. So let's see if I can measure this without blowing something up. It's a little bit difficult to do with one finger. Okay, 40. And see the speed that it's going down with. This is by discharging with 10 megohms. 41 volts, and the unit is off. Okay. It's a 35 volt capacitor. Hey, yeah. Is that a good or a bad design? I would say that you need more voltage on the specifications than the voltage you're applying to the capacitor. And this is what happens when the output voltage is more than half. Then it goes to 41. Ew! And there are no discharge resistors at all, so they stay charged for hours. The reason why I know this is I got a little unpleasant surprise before. I don't need to go into more details than that, but you can maybe imagine what happened. And this size of this baby is how many thousands of microfarad? 4,700, or is it that? Yep, so that's pretty good. What I was going to say about this 3 amp 5 volt output, that one is actually with sense. So you see the red and yellow wires here? That'll be the sense wires. It's real cool with the red wires, actually the black one. Yeah, but if you flip this cable the other way around, you can of course imagine it would have been right. So I think this is how it was intentionally designed to be, the other way around. But hey, if you start with this end and fix the cable and then oops, yeah, well, let's just flippity floppity all the wires and then it's gonna work, right? So what I wanted to do is I wanted to try and put the sense wires on the other side of the output, so the current flow this way, and then I measure the voltage on the other side, because there's almost no voltage drop in this big thick metal all the way out. But if you put the sense on the other side, then it is really a big improvement. I measure a few milliohms this way, because I was trying to put my voltmeter here, and then I still see a big drop, but the voltage drop is actually now between this tiny little piece of metal, and it's quite thin. So that is what's causing the problem. I want to try and do that and see if it's a lot better. So after I moved the sense wire, the 2 sense wires to the other side of the solder points here, I got this result. Ta-ta-ta! So that really works. Amazing how little it takes. And it's just, it didn't cost anything extra just to fix this. Anyway, let's see how this the relay system works. I got a load connected to that output, and it says 2 amps. So yes, that's 2 amps. So every time there is a little bit of a voltage on the output, it will draw 2 amps. Current is at maximum. So this is the, oh, let's see, why is this lamp always in the way? Okay, this is the voltage, output voltage, right? So when I turn up the voltage, you will see the voltage on the capacitor. This meter is measuring the voltage on the main capacitor for the board after the relay switching system. All right. Let's see if we can make this a little bit more visible, maybe. At the same time, that is difficult. All right, so when voltage goes over, this is 5, 6, 7. Did you hear the click? So that was about 7 volts output. The relay switches, and we get 23 on the capacitor. So now there's plenty of voltage available for good regulation and good ripple and all that stuff. So let's go on. It was 15, 16, 17, 18, 19. Yes. So at about 19 volts output, it's cranked up to 34. Remember, this is under 2 amp load. And then I can of course continue with the output up to 30 volts output. And I got 34, so that is perfectly fine here under load conditions. Now let's try something funny. Let's remove the load, and the voltage skyrocks all the way up to 42. Of course, there's no load on the system, right? So, and again, this capacitor is rated 35 volts, and that is the problem. So now we got 42 volts over this capacitor. And of course, when I crank down the voltage, click, but nothing happens, right? Yeah, now something actually does discharge the system. And then I go down again, click. Why did it do that? Maybe there was a little bit of a noisy bug in the pod. But anyway, voltage is not going down so fast. But that is quite funny. Now see what happens when I turn it off. So the electronics kind of shut down the discharge of this capacitor when the electronics is off. That is really smarter or not smarter, I don't know. So that is funny. Let's try again and put on the. This is just the worst way to do it. I'm sorry. Okay, so we got load, 2 amps, and now the 2 amps go through the bridge rectifier, and I just turned this on, and I can already feel it. After just a few minutes, this one gets glowing hot. I'm gonna leave it for a little bit, and let's get back and see how hot it actually gets. So I left it running just for a few minutes. So of course it's the transistor on the back that is nice and warm, but also so how hot is that? Look at that, huh? And this is only a few minutes. $100 and what? 8? Is that what it says? Or even 110? So that rectifier is just amazingly warm. Oy, oy, oy. It's right next to the capacitor and the relays. And we got metal right here. Ice cold metal. Why isn't it mounted on the metal? There's a hole for a screw. That's a little bit stupid, isn't it? That would have been so easy to do. But this is clearly not meant to work for a long time with 2 amps of load. And certainly not with 2 of them at the same time. It's just meltdown. Absolutely not a good idea. Just a few minutes of only 2.6 amps. I didn't even give it 3 amps because there's some alignment of the amp meter that is not right I believe it has something to do with those trimmers down here. Quite a lot of trimmers, and that will do voltage and amps and stuff like that, so it can read correct. I will play a little bit with this in a minute. Let's see what happens. See, this is a 100 and what? So that is quite hot, this resistor, right? 130. And that will be the sense resistor for the current. But anything else on this board is ice cold except for the rectifier. See, this is the rectifier. Let's have a look from the side. Oh, let me do the flippity floppity here. So we got a good macro, yes. -95 Celsius on the rectifier, and a little bit colder, only 60-70 on the heatsink. So the heatsink hasn't really a good contact with the rectifier. But again, oh yeah, okay. Let's look at the series regulator. Let's see if we can get a picture of that one. That's only 50. So even if you put the rectifier directly on the series regulator transistor, it will still be half the temperature. That's what I'm saying. We got a lot of metal here, and it's easy to use. And again, they didn't do that. So don't load any of the outputs at its full capacity for a long time. And I mean just a few minutes, or like 5 or 10 minutes. It's going to overheat the components and cause shorter lifetime. It is just because of super simple details that could have been avoided. And now I also put those wires here. This is much better because we don't want parallel wires that carries ripple and stuff. I'm so sorry to say this. I've been trying to adjust the amp meter on the 3 amp output, and yes, it is, this cable here is a little bit in the way. It is that one that is doing this, but the problem is the sense resistor here changes with current so much, it's just impossible to trim this at anything at all. Let me show you. Let me show you guys how bad it really is. So if I trim this to be accurate at 1 amp, this is 1 amp, right? And it's super accurate now at 1 amp. So let me give it 2 amps. This is 2 amps. That's just absolutely not good. And this is of course because this resistor is getting red, glowing hot. And then it is over driven, and its temperatures just goes away, and its specifications is not good, and of course you get this bad. And also, I don't know what to say, but that is just not acceptable to have an amp meter that is this bad. It is absolutely useless. So this resistor is definitely something you need to change to a much bigger, much more professional type. Probably mounted on metal so it can get away with the heat. Make it a 4-wire system so you will get an accurate current measurement. That is definitely what you want. And the other ones, there will be the current limit and voltage settings and all that stuff, right? But maximum current is perfect. It shuts down at 3.2, and that's exactly what I want. So far that is good. Let's put a little bit of light here so we can see how beautiful the PCB layout is real nice, and And everything else is done correctly here. And there are no other hot overloaded components at all. It's really, really good. Voltage rating, everything here, and that capacitor and all that is perfectly fine.